Hello there. Welcome back to our course on advanced quantum mechanics. This is lecture 33. Today, we will consider the situation of composite systems that consist of identical subsystems. For this, let us start with the consideration that the universe is 13.8 billion years old. Now, that means that most of the protons and the electrons in the universe are about that old. Now, do we see them aging? Do we see that protons are getting wrinkles, that perhaps they start losing some of their charge? Do we see electrons growing gray beards? No, we don't see any aging on elementary particles. Same is true for molecules, such as the water molecule. If you take a bottle of water and you keep shaking it, you keep stirring the water in there, then one might expect that the water molecules wear out. After all, they keep bumping against each other. So maybe they would wear out, but they don't. A new water molecule is exactly as good as an old water molecule. A new proton is exactly as good as an old proton. In fact, they are not distinguishable. Particles of the same species appear to be entirely indistinguishable. And that indistinguishability is property that they don't age, and that you can't put a scratch into an elementary particle. And in fact, you can't put a scratch into a water molecule either. That indistinguishability has important consequences. Consider a composite system which is made out of two copies of the same system, two electrons, two water molecules, two protons, or whatever you may want to choose as the subsystem that you replicate. So what we have here is some system A1 and some other system, let's call it A2, and they are of the same nature, like two electrons, for example, and we now consider the composite system that we may call A1, A2, but which we will actually simply call AA. Then what's the Hilbert space here? Well, the first system has a Hilbert space the second system H2, and then this one has a Hilbert space A1, and obviously they have the same nature because the two systems are indistinguishable. Now, the big system, the total system, we would expect to live on the Hilbert space HA1 tensor HA2. And that would be the case if the two subsystems were distinguishable. But it turns out that actually the Hilbert space of the system AA is smaller. It is contained in this Hilbert space, but it's smaller. Now let's see how that comes about. Assume, so here, Y. Assume that Q hat is an observable of our system A1. Then we can also measure Q hat on system A2. Why is that? Well, they're identical systems, so they must also have the same set of operators, the same set of observables that you can measure on them. For example, if there are 2 electrons, then you can measure the spin of 1 electron, but that means the other electron also must have a spin that's measurable, or the momentum, so on. So let's say Q hat is an observable, and then of both subsystems, and then what are the measurement outcomes? So then we obtain 2 measurement outcomes. And let's say we call them Q and Q tilde. See, Q and Q tilde. So these are the numbers that come out of these 2 measurements when we measure the observables, the observable on both our subsystems. Then what state does our system collapse into after we've measured that? Then what is the state afterwards? So we have now performed a measurement from the outside, right? So we have the total system here, and we have taken a measurement apparatus from the outside, and it measures the observable Q hat on this subsystem and the observable Q hat on that subsystem. But of course, since the 2 are identical, cannot be distinguished, our measurement apparatus doesn't know whether the measurement outputs that it got were from this or that subsystem. So what then is the state collapsing into? Is it the state Q tensor Q tilde? Well, that would make sense, but it could also be, is it the state Q tilde tensor Q? Right? So, for example, the measurement outcome Q could be 5, the measurement outcome Q tilde could be 7. So which state is it then? Is it the 5-7 or the 7-5 state? We cannot distinguish the 2 subsystems. Therefore, we do not know whether we measure that value on the first or on the second system, whether we measure this value on the first or on the second system. We only know we measured both values, but we don't know which system to assign them to. Therefore, one might wonder, well, does it not matter? Maybe I could use this state or that state, and it doesn't matter. Could that possibly be the case? No, that's not it. Obviously, these are different states, and you might get different predictions if you use them. No, we have to implement what we know, which is we know the indistinguishability, and therefore we know that the state psi after has to have the property that if we do a swap, and we will have to see what that means, if we do a swap on that state, where we swap the roles of the 2 subsystems, where we swap all references to the 2 subsystems, then that should be the same state. So this should be psi after again. Now, remember that when we have a pure state, you can always multiply it with a phase, and it doesn't make a difference for the predictions. That means we have to allow that there is a phase in here. So this could be e to the power I alpha phase with alpha some number between 0 and 2 pi. So we know that we have indistinguishability, And therefore, swapping the role of the two subsystems ought to give us the same state up to possibly a phase. Now, normally, as I said, phases don't matter. And so we can freely put phases there in front of a pure state or not there. That's okay. But it turns out that this particular condition is a powerful one. It does matter because not every state has this property. It depends which phase you choose, which states in the Hilbert space have that property. In order to make this more accurate now, in order to make this precise, we have to define what this is. What exactly do we mean by the swap of subsystems? Well, we mean, of course, that if you exchange the two tensor factors there. But what is the physics of it? The mathematics of it is that we swap the two tensor factors. The first tensor factor corresponds mathematically to the first subsystem. The second tensor factor corresponds mathematically to the second subsystem. But remember that the physics is such that we cannot distinguish the first from the second subsystem. You see, when we draw a picture like this, and we say, okay, A1 is an electron, A2 is an electron, then you might intuitively think, okay, I know A1 sits here, A2 sits there. But by assumption, the two are not distinguishable, which means that we do know we have two electrons. And we may know that we are likely to find one here and likely to find one there, if this is a spatial map. But it doesn't mean that we find the first one here and the second one there. We still don't know which is which. So what exactly is the physics of swapping two tensor factors? What's the physics of swapping the role of two subsystems? This is surprisingly a pretty intricate question, and it's answered by the following proposition. The swap of two subsystems amounts to a 2 pi rotation. Now, to prove this, we would need to go into the representation theory of the rotation group. And that would take us a few hours to do properly. I would have to tell you about the SO3 rotation group, and then its universal covering group, SU2, and so on. I think that this material will be covered actually in the next lecture, in the next course in the winter term taught by Eduardo Martinez. For now though, let me just give you an intuition for this. An intuition that goes back, going back to Arthur Broyles and Richard Feynman. Now, Feynman popularized this, but it really goes back to Broyles, who found this earlier, even though Broyles was younger than Feynman. Okay, so imagine you have two systems, one here and one there. And you want to swap the two systems. So this one moves over here and that one moves over there. Okay, how could that possibly correspond to a 2 pi rotation? Well, let's see. This one rotates like 180 degrees and that one rotates 180 degrees. So maybe it's plausible that the whole thing is a rotation of 360 degrees. or is it? Well, this is where Feynman's experiment comes in. I took off my belt to do Feynman's experiment. This is a belt, and you see it doesn't have a twist in it. What do I mean by a twist? Well, let me turn it around a bit like this. You see, now it has a twist in it of, I don't know how many degrees, maybe 720 or something. Okay, so Feynman now says, make sure that the belt doesn't have a twist in it at the start of the experiment. So, see, here's the belt, no twist in it. Okay, no twist. And now we interchange the two particles. So we move this like this, and you see I'm not rotating here in any way. So I'm just passing them past each other, swapping hands, and there we go. All right, so now they have changed places. And you see, obviously there's a twist in the belt now. But how much of a twist is it? Well, let's see. I will now rotate this end until there's no more twist. And let's keep track of how often I will have to rotate this. By what angle will I have to rotate this end of the belt? So I turn it now by 180 degrees. All right, this is 180 degrees. Let's check if we still have a twist in it. It looks like a twist, and we do have a twist. It doesn't go away if I stretch it, right? All right, now let's keep turning it. Another rotation by 180 degrees. Now we are here. Let's see, it looks as if it was twisted, but let me just pull it a little bit, and you see, no, it's no longer twisted at all. It's fine, there's no more twist in this. So we've untwisted it by a rotation here of 2 pi. Now that's just an intuition, and the actual calculation would require some group theory. So our original question was this: when we swap the role of two subsystems, then we may acquire a phase factor of e to the power I alpha if the two subsystems are identical. And we were wondering, what could e to the power I alpha be? Now, with this little belt experiment and the math behind it, we have reduced it to the question of what can happen if we rotate our two subsystems about each other so that they swap places. And now we have reduced it to the mathematical problem associated with the representation theory of the permutation group. Of the rotation group. So now the representation theory of the rotation group yields, and I wish we had a few more hours so that I could explain to you in all detail how that happens. But let me just give you the gist of it. The representation theory of the permutation group tells us that there are only few possibilities. Well, yields 3, it's not a 3, yields 3 possibilities. Namely, first, alpha equal to 0, i.e. EI alpha equal to 1. And that would be, of course, you know, the case of bosonic. Bosonic identical systems. And then secondly, there's the case where alpha is equal to pi, i.e. EI alpha is equal to -1, and that is called the case of fermionic identical systems. And then thirdly, there's also the case where alpha is an element of 0 and 2 pi, but alpha is not equal to either 0 or pi. And that would be called the case of anionic identical systems. Now, this last case here, it follows from the mathematics of the representation theory of the rotation group, can only occur in 1+1 and 1+2 dimensions. Now, you might think, okay, that rules this out. There shouldn't be any anions. But you may have heard of anions. So how come people are studying anions? Well, the reason is that there are, even though space-time has at least 3 space and 1 time dimension, there are effectively lower dimensional systems, such as e.g. possibly, I should say this is not confirmed, e.g. possibly in layered high temperature superconductors. It could also arise in the, you see, layered high temperature superconductors are sandwich type materials. They are ceramics, where a copper oxide layer is alternating with an insulating layer and then another copper oxide layer. I mean, these are most of the high temperature superconductors that have this structure. And these layers are, effectively 1 atom thick. And so they are effectively 2-dimensional. With a good approximation, they are 2-dimensional. And it could be that anions might play a role in there. It has been considered. But then there are other effectively 2-dimensional systems, for example, systems in which the quantum Hall effect occurs. Then there's graphene, which is carbon, 1 layer thick carbon sheet. So anions are not completely ruled out. They are mathematically definitely well studied. And there can be at least effectively low-dimensional systems. And I will say a little bit more about this in a moment. So, but let us ask, how could alpha not be 0? Just coming back to this question, how could it be that when you rotate something by 2 pi, you don't get back to where you started? Now, the previous intuition, the one with the belt, indicated that it is possible, because when you exchange the 2 ends of a belt, then definitely you're not back to where you started, right? You are at this position of the belt now, and yet you've already accumulated a phase of, sorry, I don't know about the phase, but you've already accumulated a 2 pi rotation. But let's see, is there an instance where you rotate something by 2 pi, and so you rotate one thing by 2 pi and you don't come back to where you started? And only if you do another 2 pi rotation, you get back to where you started. This would be the case where alpha is pi, right? And let's ask, how could it be that alpha is pi? Alpha is pi means e to the power I alpha is -1. It's a fermionic case where if you rotate twice, it gets back to where you started. Now here too is an intuition, and I think it goes back to Feynman. I'm not exactly sure where I picked it up, but I think it goes back to Feynman. And that's another little experiment that you can do at home. So this experiment is going to be a little rough, and you might find yourself in knots when you do it. Let me give it a shot. So I want to rotate this pen here in my hand. That's the pen with which I'm writing. I want to rotate that pen twice by 360 degrees. So it's going to rotate like this once and then twice. All right. And I will do it in such a way that illustrates that after having done one rotation, I haven't really returned to the previous state yet. And it takes me 2 full rotations to get there. So what I will do is I will rotate with my arm this pen. And I will do it once under my shoulder, and then I keep rotating above the shoulder, right? And after I've done the first rotation, I won't be in the same state. I might lose control over my arm at that point. Unless you're very dexterous, you might find this challenging. So here's the pen, it's pointing towards you, right? Now I'm rotating it under my shoulder. Look at the orientation of the rotation, right? I keep going like this, and now it's pointing to you again. I've done 360 degrees, but my shoulder is struggling here. And now I keep rotating in the same direction, and I'm coming back, and it's like that. The whole point of this exercise is to show that if you rotate once and then keep going, you did 2 rotations and you're back to where you started, but after the first rotation, you're not back to where you started. All of this is not proving, this is not to prove that electrons do this or other fermions do this. This is just to illustrate that the rotation group is quite non-trivial, and there are representations where a 4 pi rotation is necessary in order to return to the initial state. Now let me make a bit of a comment here about anions. So question, what is the mass of anions? So alpha not equal 0, not equal pi. Well, this is actually pretty cool math. It works like this. Remember, when you have a vector with coefficients, let's call them V1, V2, V3, and then here you have the rotation matrix with entries R11, R12, R13, R21, etc., etc. Then you get the rotated vector here, which would be W1, W2, W3, and this matrix here would be said to be an element of, let's say, the rotation group SO3. Now, what's the condition for the matrix to be an element of the rotation group? The condition is, if this thing is called R, R has to be such, my handwriting has to be such that the length of these vectors stays the same. So such that square root of vi squared, sum over I, is equal to the sum over the w. And also the angles between vectors will have to be preserved, right? It's not so important exactly what the conditions are. I hope you've seen the rotation group before. You know, this S means that the determinant has to be 1 and so on. The point I want to make here is that we should notice that the rotation group elements, these matrices, conserve more than just the length and angles of vectors. Namely, they also preserve, these rotation matrices preserve also the commutation relations among these V. So if the VI commute, then we also have that the WI commute. Now this is fairly trivial, right? Because these are commutative, I mean, these are numbers usually. And this matrix has numbers as its matrix elements usually. And then these three will be just numbers again. And so they will commute just because all of these and all of those commute. But we also notice that if the VI anti-commute, and some of you may know that this is what comes up in fermionic systems, i.e. if the VI Vj plus Vj Vi equals 0, so there's a plus sign instead of a minus sign, then, well, then it follows that also the Wi, that also the Wi will anti-commute. The conclusion here is that the rotation group, and in fact every Lie group, preserves both bosonic commutation relations and fermionic anti-commutation relations. And that's fine because usually in physics we just work with Lie groups, and we have bosons and we have fermions. So what about anions? Well, for anions, we have that when we interchange V1 and V2, we pick up a phase. And here is what that means. So anions, they typically have commutation relations of the form V1, V2 minus e to the power I alpha V2, V1 equal to 0, etc. for the other commutation, for the other components. Then we need conservation of the commutation rules. So we need that then also W1, W2 minus EI alpha W2, W1 equal to 0. And this means that the Rij RAB commutator is generally not 0. Specific commutation relations are required. And what do we obtain? We obtain what is called quantum groups. So quantum groups are obtained by requiring that we have a matrix which, when acting on a vector with components that are either commuting or anti-commuting, or, and this is what makes it really anionic, if they don't commute or anti-commute but have this e to the power I alpha commutation, then after the action of that matrix, we want the same commutation relations again. That gives you what is called a quantum group, and that's not the mathematical expression. The mathematical expression is that it is a quasi-triangular Hopf algebra. I actually worked on these things in my PhD. All right. We will stay here. Here, focus on bosons and fermions only. Focus on bosons and fermions. I just wanted to give you an idea of what you expect if you happen to work in lower dimensional systems, because in lower dimensional systems, always keep your eyes out on the possibility that there might be a statistics that is not that of bosons or fermions. Of course, the electrons in a lower dimensional system in condensed matter will still obey Fermi statistics because they're fermions. But, and so do the protons and so on. But there are collective excitations and quasi-particles in condensed matter systems, which are effective particles made out of the crystal, made out of what's going on else in the crystal, such as phonons and spin waves and so on, or holes in a semiconductor. And there's always the possibility that these quasi-particles or collective excitations might obey a non-trivial statistics, so might obey a non-Bose, non-fermionic statistics. Okay, let's look at the consequences now of having Bose or Fermi statistics. So examples. Let's start with the Bose case. So we have alpha equal to 0, and so we have that the swap operation acting on a physical state has to be the same state again. And let's say we have 2 copies of system A, and let's say system A has a 2-dimensional Hilbert space. System A has 2-dimensional Hilbert space, H superscript A. You may wonder, how come we can have a Hilbert space of 2 dimensions? Why don't all Hilbert spaces have infinite dimensions in physics, given that the XP commutation relations can only be represented on infinite dimensional Hilbert spaces? True, nature works with infinite dimensional Hilbert spaces as far as we know. And yet, it is possible to restrict attention to finite dimensional Hilbert spaces for 2 reasons. One is that we may not have energy enough to excite our system to higher than the first excited state. Maybe there is just enough energy for the ground state in the first excited state. In that case, we can forget about all the other dimensions. Another case is, or maybe the first 5 excited state or whatever, and then you would have a 6-dimensional Hilbert space effectively. Another situation is that there are natural subsystems that we haven't covered yet, which are finite dimensional, such as the spin of an electron or the spin of a quark. It is always a 2-dimensional Hilbert space. And that if we just look at the spin of an electron, that would be a 2-dimensional system. All right, so let's say we have 2 systems, identical, bosonic, and each one of these systems has 2 energy levels, or it has a 2-dimensional Hilbert space. The 2 states, 2 basis states in there might, I mean, all the states in the Hilbert space may be of the same energy, but we just want to assume that the Hilbert space has 2 dimensions. And let's say it is spanned by a basis of vectors A1 and A2. All right, this means then the Hilbert space HA tensor HA is spanned, for example, by this basis, by this ON basis. Well, it's the basis vectors A1, tensor A1, and I will now drop the tensor symbol. So we have A1, A2, and A2, A1, and A2, A2. We can easily verify that these four vectors are orthogonal to each other, and if the AI are normalized, then so are these four basis vectors. So this means that this Hilbert space has 4 dimensions. So the dimension of HA, tensor HA, is equal to 4. However, it turns out that because the two systems are identical, they cannot access the full 4 dimensions of this Hilbert space. In fact, they can only access the subspace of those vectors in the Hilbert space which obey this condition. The swap gives us the same vector again. So we have to say, but the Hilbert space of our system AA bosonic is smaller and spanned by these 3 orthonormal basis vectors. Namely, well, there is the vector A1, A1. Clearly, if we apply the swap operation on it, then it's still A1, A1. And then there is A2, A2. And then there is 1 over square root of 2, A1, A2 plus A2, A1. Okay, but this remaining basis vector namely the antisymmetric combination here is not in our Hilbert space. So 1 over square root of 2, A1, A2 minus A2, A1 obeys that the swap of it, so if you put this in here, is equal to, I mean, let's call this thing psi, right? So if we call this here psi, is minus psi. So therefore is not in H bosonic of AA. And in fact, what we see is, notice that this vector here, psi above, is the only dimension, spans the only dimension in the Hilbert space when the two subsystems are fermionic, are identical fermions. So what we see is that the Hilbert space is either 3-dimensional for identical bosons, or it's 1-dimensional for identical fermions. And what we see here is also that in the fermionic case, we see that if the first particle is in the state A1, then the second particle has to be in the state A2, or if we find A2 for the first particle, then the second has to be in state A1, and therefore we see here the Pauli exclusion principle at work. We see the Pauli exclusion principle for identical fermions. Okay, so This was the bosonic case up to here, and up from here is the fermionic case. Okay, so this is the remaining basis vector there. Now, in general, of course, what we have is, this was just for 2 dimensions, but in general, we have that for distinguishable subsystems, so distinguishable, we have that the Hilbert space is HA tensor HA. Actually, we would call them A and B in this case. But then in the case of bosonic subsystems, we have that this is just the symmetrized version of, or it's the subspace of symmetric vectors in this Hilbert space. It was 3-dimensional here. And then the fermionic case consists of the anti-symmetric part of that big Hilbert space. Now, what consequences does this have? Of course, you've heard of the consequences of Bose and Fermi statistics. Let me give you a quick overview that hopefully points a little bit beyond what you've already seen. So, consequences. Let's start with the case of fermions. Well, the key consequence of Fermi statistics, of particles being identical and fermions, is that there is then Fermi pressure. And what does that mean? This means that in atoms, the shells fill up. Right? So if electrons were bosons, then in a carbon atom, for example, all the electrons would want to occupy the lowest energy state, but they can't because they're fermions. So they fill up the lowest energy states of the carbon until there are no more electrons to put there. So we have the shell filling because of that. Now, what happens if you put atoms together to form a crystal, and especially a metal? Now, in the case of a metal, what distinguishes metal from many other materials is that in a metal, the electrons that would normally be in the outermost shells of their atoms are actually no longer tied to their nuclei. These electrons become adventurous and they travel throughout the crystal, throughout the metal. So the outer electrons are shared by the entire crystal. They're no longer just localized to their home nucleus, so to speak. So we have a kind of an electron gas that is in the metal. Most electrons are still tied to their nuclei, but the outermost ones are actually delocalized. And what happens to the outer shells? You see, when you take a metal and you heat it up so that it evaporates, then you have the individual metal atoms flying around. You have a metal gas. And each one of these atoms, for example, iron atoms will have its atomic shells that will be filled by its electrons until the highest shell is filled, you can fill with so many electrons. And now imagine the reverse process where they start condensing again into the crystal. Then as these atoms form a crystal, they start interacting with each other, and what used to be the outermost shells still occupied by electrons, they melt together and they form what are the bands in the electronic bands in the crystal. And what do the electrons do? Well, they fill these bands in the crystal until there are no more electrons to fill up more. Right? It's all because of the Fermi pressure that electrons cannot be in the same state. So they fill these bands until they reach the maximum that they can fill given the number of electrons that are available there, so that the whole metal becomes neutral or is neutral. These are the so-called Bloch energy bands. Now, the electrons that are at the highest energy level in the crystal, they are said to be at the Fermi energy level. This is the analog of the electron that's the outermost electron for an atom, but now for an entire crystal. And it turns out that these electrons that are at the Fermi level of energy, that are all the lower energy states in the crystal are already taken by other electrons. So those electrons that are at the highest energy there, they would never be at such a high energy if it wasn't for them being fermions and having no other choice. If electrons were bosons, then they would of course all want to congregate in the lowest energy levels that are available in the crystal. You could still make them, even if they were bosons, you could still make them go into high energy levels. But you would have to heat up your crystal to do this, right? Because if you heat up a system, then its higher energetic energy levels are going to be more likely to be occupied. And the higher you make the temperature, the more it becomes reasonable to expect that some of the higher energy levels will be occupied. And you can ask, how high would the energy of a crystal have to be such that if electrons were bosons, they would actually occupy such high energetic levels? And the surprising answer is that it would have to be in the tens of thousands of Kelvin. So the only reason why electrons are at such high energy states in the crystal is that they have no other choice because of the Pauli exclusion principle, because of the Fermi pressure. So bands fill up. And then there are neutron stars. Now, neutron stars. Neutrons are fermions. And if you compress them, then the Fermi pressure kicks in. And that is literally a pressure. And it is the Fermi pressure that makes the neutron stars resist gravity. Fermi pressure holds a neutron star up against gravity. Well, one can calculate what that pressure is. And if you make a neutron star too heavy, if you keep throwing garbage onto a neutron star and it becomes heavier and heavier, then eventually the Fermi pressure is not enough and it will become a black hole. That's been calculated, and the threshold has been more or less confirmed experimentally. It's pretty impressive stuff. Now, what about bosons? What's the consequence of bosonic behavior in practice? Well, there are lots of consequences. And in particular, just like fermions cannot be in the same state, bosons actually want to be in the same state. Not only can they be, it's preferred for them to be in the same state. Not necessary, but preferred. So want or prefer to be in the same state. Now, that means it means thermodynamically they want to be. If you expose a bunch of identical bosons to a heat bath, then they are more likely to be in the same state than they would be if they were not bosons. Let us look at the very, very simplest case. Consider case of above. So where the dimension of each of these Hilbert spaces of the identical bosons is just 2. Then what we have is that if A1 and A2, the two subsystems, are distinguishable, then these 4 states are possible, namely the 4 basis vectors, A1, and then A2, but also A1, A2, and A2, A1. They're all possible, but notice that these 2 are such that the first system is in the same state as the second system. And here too, the first system is in the same state as the second system. So both subsystems, let me write it out. Both subsystems, these are 2 states in which both subsystems are in the same state. Here, they are in different states, right? Because if this is the state of the total system, then one subsystem is in that state, the other one is in that state. It's a different one here too. Now, assume a heat bath. But first of all, assume all states are of equal energy. In the homework, I'll let you calculate what happens if they're not of equal energy. But let's for now imagine that all states have equal energy. For example, it could be spin up or spin down and there's no magnetic field. In that case, they are of equal energy. So assume that all states are of equal energy. Therefore, equally likely. So therefore, the probability for the 2 subsystems to be in the same state is equal to the probability that they are in different states. So you see, the probability for A1, A2 in same state is equal to a quarter plus a quarter, which is 1/2, because this one has a probability of a quarter, that one has a probability of a quarter, and all of them do, because they're each equally likely to be found. All right, so the probability that each subsystem is in the same state is 1/2. And the probability that they are not, so probability for A1, A2 in different state is also 1/2. Okay, so this is the case where the two subsystems are distinguishable. But what if they're not distinguishable? Here, not H, A1 and A2 bosonic. Then only 3 states are possible. So now we have that we have A1, we have A2, A2. The system could also be in the state 1 over square root of 2, A1, A2 plus A2, A1. And if each state has same energy, then same probability. And it doesn't matter what the temperature of the heat bath is, right? The T of 1/3 each. But this means that the probability that A1, A2 are in the same state is equal to 1/3 plus 1/3 is 2/3. Why is that? Because it's this state is a state where both subsystems are in the same state, and that's a state where both subsystems are in the same state. And each one of these states is occurring when in contact with the heat bath with a probability of 1/3. So in total, the probability that we are in a state where both subsystems are in the same state is 2/3. Whereas the probability for them to be in a different state, A1, A2 in different state is equal to 1/3. So this is enhanced. It used to be that it was 1/2 the probability, but now we see it's enhanced. And this enhancement changes when we have large systems of identical bosons. In fact, it can get completely out of hand. Let me illustrate. Now let's look at large systems. Large identical boson, no. Large number of identical bosons. Well, in this case, what do we have? Case 1. Let's say we do in red again the distinguishable case, just so that we know what we can compare with. Distinguishable subsystems. Subsystems. Let's call them AI. So we have lots of them now. With energy levels well, each of these systems has energy levels that we may call En. Okay. So then, what is the probability for finding the number n0 of bosons in the ground state, n1 in the first excited state, n2 in the in the second excited state, etc. So this would be number of bosons in second excited state. What is that? Well, up to a normalization factor, we know that this is proportional to e to the power of, and then we have this Boltzmann factor that we calculated when we calculated thermal states. Namely, this is the energy, which is the number of bosons in the ith excited state, sum over I, times the energy level of the ith excited state. And we sum all of that over all possible excitation levels. That's the total energy that our state has. And we divide that then by kT. But there can be, in principle, lots of different states that all have the same energy, right? You can add up to the same energy in many different ways. So this is, there's a prefactor here, which is the number of states for number of states with N0, N1, N2, N3, etc. Sorry, this is not intended. Okay. So you see, it could be that, let's say we have all of the particles one-fold excited, except for one particle that is in the second excited state. That's a possibility. But there's not just one state that does this. No. There are a lot of states, because it could be any one of these subsystems that is in the second excited state, and all the remaining ones are in the first excited state. So there are plenty of states, plenty of orthogonal states, which each have this number of subsystems in the ground state, that number of subsystems in the first excited state, that number of subsystems in their second excited state, etc. And this here is a combinatorial factor. This has to do with factorials and, you know, n choose m or something like that. When you calculate how many states are there that have this property, right? Now, this is obtained from what we knew earlier, right? We have that, oh, I should write it here. Recall the density matrix is given by e to the power minus the Hamiltonian divided by kT, and then you have to divide by the trace of e to the power minus the Hamiltonian divided by kT in order to make the whole thing normalized. And what we are calculating here are the elements of the density matrix on its diagonal. And we are not distinguishing here which of the subsystems are in which excited state, which is counting how many of them. That's why we get this combinatorial factor here. This comes from the degeneracy of the Hamiltonian. The same eigenvalue can occur many different times because many different subsystems can contribute in different ways to the same total energy of the system. And this is the number of possibilities by which you can arrive at the same total energy over here. All right, so how big is this number? Well, if the number of bosons is huge, and this number is gigantic, right? So grows quickly, grows fast, because it's combinatorial. And what about this? Well, as the energy of our system is increasing, as we require more and more of our identical bosons to be in excited states, if we do require that, then this adds up to this energy here, and we see it's exponentially suppressed. So this decays fast. And what you see here is the drama of thermodynamics, of quantum thermodynamics unfolding. We have here the competition between something that's decaying very fast, namely this. You see, it's very unlikely for a system to be in a high energetic state. It's exponentially suppressed with the amount of energy. But also, there are many, many, many possible states that you can write down that have a given energy, because you can arrive at the same energy level by combining the energies of the many, many subsystems in many, many different ways. So overall, you have that there's a huge number competing with a very small number. And as it turns out, together that product is reasonable. And what do I mean by that? Well, we know what comes out of this because we've calculated it already. Remember, we've calculated what happens if you take one system and couple it to a heat bath. We calculated what this is, I mean, for example, for a harmonic oscillator. And now what if you had a huge number of independent, distinguishable harmonic oscillators that each couple to that heat bath? Well, if they're truly distinguishable and truly not interacting with each other, then simply each one of them behaves normally and doesn't care about the others. And that means that if you have lots of quantum systems and they are distinguishable and they don't interact with each other, then if you work out what the growth of this combinatorial factor is and the decay of that exponential here, they just cancel each other in such a way that you simply get that every system is behaving normally. And there's no interaction, and you can simply calculate for each one of your subsystems what its density matrix is for this given heat bath, and then the total density matrix is just going to be the product of all those, the tensor product of all those tensor products of the subsystems. So that's pretty straightforward. And we see how this is just compensating for that to give you the ordinary quantum mechanics of a quantum mechanical system in contact with a heat bath. But what happens if our particles, what happens if the AI, the subsystems, are identical bosons? You see, everything changes in this case. And the reason is that this formula would still be holding true with this decay over there. It's decaying so fast as the energy that we are looking at is increasing. That state becomes very unlikely. But this prefactor that used to grow so fast doesn't anymore. This prefactor collapses for identical bosons. Because we need to symmetrize over all of the subsystems. The only states that can have particular energies that we choose are states which have this symmetry property that if you interchange any two of its subsystems, it must still be the same state. And that reduces that number, it collapses it. And what that means is that now we still have that elevated energies are enormously suppressed, but there's no compensating combinatorial factor that would drive it up again. And instead what we have is Bose-Einstein condensation. Combinatorial factor collapses. Therefore, excited states are exponentially suppressed. And therefore, what we have is Bose-Einstein condensation. In the sense that almost all of the bosons will be in the ground state, and all other states, well, yes, a few of them might be in excited state, but it's quite suppressed because of this exponential that has nothing to oppose it anymore. There's no big combinatorial factor that opposes that. And experimentally, this is observed. For example, in 1995, it was observed in helium-4. Helium-4 is an isotope of helium, where you have 2 protons and 2 neutrons, but there's also helium-3. Now, helium-4 is bosonic. Helium-3 is fermionic. So for helium-3, we would not expect, perhaps, that Bose-Einstein condensation can occur, but helium-3 atoms can combine, and 2 helium-3 atoms together have an even number of protons and neutrons. And so they form a bosonic particle, a bosonic system together. And those bosonic systems of 2 helium-3 can actually condense, Bose-Einstein condense then. And that's not the only case. Okay, also helium-3 in pairs. And then related to that, we also have superconductivity. And again, it would seem unlikely because electrons are fermions. How can they condense into a Bose-Einstein condensate? And it's actually a highly non-trivial story. Electrons too can team up to form Cooper pairs, and then these Cooper pairs are bosonic and they can condense. And then, of course, the simple calculation that I just indicated here is not quite valid, right? Because you see, the electrons have to team up in order to form so-called Cooper pairs, which are then bosons, which can then condense into a Bose-Einstein condensate. And electrons don't want to team up in pairs because electrons are negatively charged, they repel each other. Why would they team up in pairs? Now, it's known that for low temperature superconductors, electrons team up in Cooper pairs because they do not only have electrostatic repulsion, but there's also an effective attraction between electrons in a suitable crystal because the electrons can exchange not only photons, which is repelling them, but they can also exchange phonons. And phonons convey an attractive force. And for low enough temperatures, this can bind electrons together in Cooper pairs, which are then bosonic, which can then condense. The whole story is much more complicated than what I told you here. But the principle is that once you have identical bosons, they can then Bose-Einstein condense. One of the biggest open problems in physics is related to this, which is that experimentally, we know that high temperature superconductors can be built. They can reach transition temperatures of 100 Kelvin and with sufficient pressure, even 150 Kelvin. And there are some systems that have enormous pressures and then undergo a superconducting phase turn even at room temperature. What we do not understand at all at the moment is how electrons can form Cooper pairs at such high temperatures. The usual phonon, that is quantized lattice vibration, induced attraction between electrons probably doesn't work at high temperatures. At least we don't have no theoretical way of understanding this, making it work now. So I just want to leave you with this, that there is this challenge to understand why electrons team up to form Cooper pairs at temperatures that are too high to be explainable by the traditional theory of superconductivity, which is thought to explain superconductivity only up to about 10 Kelvin. It's one of the biggest challenges. I've also worked on this. Many people have worked on that. Nobody has quite figured it out yet. It may be something that you may want to work on. The benefit of superconductivity at room temperature, I probably don't have to explain to you. That would be enormous. All right, so this is as far as we got today. See you then.